In this video, we are going to be investigating a stack buffer overflow vulnerability on this Linksys router. I will first briefly explain the vulnerable source code portions. Next, I will demonstrate that we are able to crash the router. Finally, we will go on to perform dynamic analysis to investigate the memory behaviors of the crash. Feel free to skip ahead using the timestamps I have provided. The stack overflow vulnerability is present in this function found in the httpd binary file, which calls a sprintf function to create a string variable named len_ip_addr_x, where x is a value ranging from 0 to 3. This variable is used to retrieve user input via the get_cgi function before concatenating it directly into a new variable via the stringcat function without validation. So let's first confirm that the router is up and running. So you can send a following request from our attacker Raspberry Pi machine to the router at this particular IP address over here. So when you run it with the verbose flag, which means just to give out more information when this command is being ran, and you can see a response. Okay, even though it's 401 unauthorized, but it's still a successful response from the router, which means it's running. Okay, so now I brought up another terminal on the top with the payload, as you can see over here. So the important field would be over here, len IP address 3 with a Python string that crafts 102 characters A. Okay, so now when you send it to the router once again at this IP address, invalid value. Okay, ignore this for now. But when we go back and send the same request, it will not be able to respond. This is because we have successfully crashed the server. Okay, so to perform dynamic analysis, I have here a console on the router itself. So first you can run this command, okay, to look for the process ID of the vulnerable httpd binary. Next, you can start the gdb server on router IP on port 8888 attached to 1215, which is the process ID of the httpd binary. Start it, okay, it will start. Now go on to our attacker machine and we can start a gdb console using this gdb multi-arch tool. Okay, start it. Alright, let me just clear screen a little bit. Okay, so we have to set the few important configurations. First, we have to set the architecture to be MIPS, which is what is running on the router. Next, endian little to indicate little endian. And lastly, you can connect to the remote gdb server using this command over here. So now you can see we have connected to it. After it's done, you can run continue to run the server. Now let's set a breakpoint on this line over here, which is within the validate len IP address function, right after it returns from this function over here. So usually you can simply type this command over here at the memory address in gdb to set a breakpoint, but somehow this does not work on this router. So instead we have to manually insert a breakpoint on this httpd binary using a custom method. So from the attacker machine, okay, let's exit out from here first. Clear screen. Okay, so first let's make a copy of the httpd binary and rename it to something useful. Next, we run this function to insert a breakpoint, which is basically just no-op instructions into this binary we've created previously at the specified memory address. So this should be changed to where we wish to insert it, which will be this memory address value over here. Okay, run it and you can see it works. So once we have created the patch binary, we can start the Python server on port 8888 to host the file. Go back to our router console. Okay, clear screen once again. We send a request to the attacker machine at this IP address to retrieve the created binary and output it into a temporary httpd directory. So okay, you retrieve. Now give it the execute permissions. Now, as you can see, we still have the old one running over here, the old httpd binary. So we have to, sorry, I can't type, log httpd and start the new one. Okay, so again we see the new httpd binary has started at this process ID. Right afterwards, we start the gdb server on the same port and attach it to over here 1347. Go back to attacker machine. Let's start once again the gdb multi-arch console. Okay, shell clear target remote 192.168.1.1.8888. As you can see at the top over there, and continue. And now we are running the patch binary with a breakpoint set. Okay, so back to the attacker machine. This payload once again, to the first lane IP address parameter value A, B, and C to the subsequent ones, and to the final one, the Python 3 string with 102 characters A. So now we can send it, and to trigger the breakpoint, we have to first identify the process ID 1536. Then we send the stop signal to trigger the breakpoint. And when we run it, you can see the screen over here changes. Okay, clear screen. Now let's run this command over here, telescope, which basically just allows us to view stack pointer, which is basically just a particular index in the stack, and lists out L30. So as you can see, this is the vulnerable buffer address that we have overwritten A, B, and C from the first three len_IP address parameter, and then 102 A's over here. So a crash alone will not be that useful. As you can see over here, we have a memory diagram of the validate len IP address function. So we can calculate the offset between the buffer that is vulnerable to the stack-based buffer overflow and a special memory address RA over here, known as the return address. So this address basically controls the next function the program calls right after it exits from the current function. And if we are able to override it with an address, we can trick the program to execute a function of our choice. Stay tuned for the next video, where I will demonstrate how we can convert this controlled crash into remote code execution using the ROP and return to libc techniques.